Hello everybody, and welcome to the webinar today. Thanks for joining us. We'd like to give a special thanks to Electro-Optics, who has organized this webinar. We thank their support. We thank them for their support. So why are we all here today? We want to explain how optical replication can provide cost benefits, especially when using aspheric and freeform mirrors. This applies to more than just A-spheres, but that's going to be the general focus of our talk today. So who is Spectrum Scientific? We were founded in 2004, and we've been providing image quality replica optics since then. So I want to be clear that the optics we're talking about today are mirrors, reflective optics, not transmissive optics. These are high performance imaging optics with low surface roughness, high specularity, and precise surface figure. We will be discussing some other methods of replicated optics or types of replications. So where does replication fit in to other manufacturing technologies for A-spheres? We'll be addressing that as we'll be addressing material benefits, some optical specification advantages, optomechanical advantages, and we will be showing some real-world data of surface figure and surface roughness and some case studies on how replication has greatly improved the optical performance for some of our customers. We'll be addressing freeforms. That seems to be a really hot topic right now, and for good reason. And we'll talk about the advantages of using freeform mirrors and the considerations when you are using freeform mirrors, so that from the design phase you can get started off on the right foot and not get designed into a corner. Ultimately, we just want to lower the cost of your aspheric components, so ultimately your instrument cost will go down and your production costs as well. So I guess I'll go to the next slide now. Here's some examples of the types of optics that Spectrum Scientific offers. Diffraction gratings is a good one to start with because on a side note, historically the replication process was first developed many decades ago in order to replicate diffraction gratings. Those of you who understand diffraction gratings know that the groove profiles are very particular, very important, and the shapes of those grooves is important to maintain, and they're very fine features, submicron features on the groove of each diffraction grating must be maintained. So it's inherently a high fidelity process, and that was done back in the 50s is when that kind of started. But since then, the replication technology has accommodated optics such as hollow retroreflectors, off-axis parabolas, ellipsoids, and now freeform mirrors. So with that, let's get to the next slide and get into a little more description about the markets we go into. For most optics companies, we all kind of touch on these all these industries. That's the great part about being in optics is as an optical component manufacturer, we find ourselves helping the life sciences. We do some stuff for aerospace. We've had stuff launch in space. Industrial applications, analytical instrumentation, telecommunications, and etc. So we cover all those industries as most optical component manufacturers do. Here's a nice overview, a schematic of the optical transfer process. You can see we start out with a master tool and make copies of that down to the final product. It's basically, to put it in a nutshell, the replication process is a manufacturing method where we can transfer the pristine optical surface onto a low-cost substrate, and that's where your cost advantage occurs. This allows for the manufacture of hundreds or thousands of copies from one tool, and this diagram kind of shows how you leverage that. So we've got a few different methods of making aspheric optics. Diamond turning. MRF is magnetorheological fluid. That's a very kind of the most advanced polishing technique these days, and it provides some very nice stuff. And then there's hand figured stuff. I mean, in the old days, before they had the machines that are available now in the CNC tools, things were hand figured. Those optics are very high precision, and those methods provide very nice optics indeed. While we're on the topic of replication, we should talk a little bit about molded optics. Now, these are usually transmission optics. Plastic injection molding and glass pressing is a common method to produce aspherics, mostly lenses. It's very low cost, very high volume, but it doesn't really have the precision for all imaging application. It has its, like all technologies, it has its limitations. And again, we primarily do reflective optics, optical mirrors, and so the precision needs to be quite high for imaging applications. Let me see if I'm missing anything in my notes here. Turn to the table a bit. So for diamond turning, if you're going to buy, whether it's one mirror, less than 10 mirrors, or many mirrors, the cost is going to change drastically. So the unit cost in high volume can be maybe $1,000, maybe $500, in that range. But if you just want 5 or 10 diamond turn mirrors, it's common. Depending on the complexity of the mirror, it could be $25,000 or more. And the same thing with glass MRF. That's a very precise technique. A lot of time on the machine, and you can see the price can be very high. Again, depending on the complexity of the mirror, making the originals, I call that original manufacturing, or the making of originals. If we go to the next column real quick, the scalability for diamond turning and glass MRF, scalability probably means buying a new machine. Typically, with diamond turning, you might be able to gang up several parts in one run, but it's probably hours on the machine for that run. And the best, the most direct way to scale up is more man hours on that machine, or buy or a capital cost investment of buying more diamond turning machines, or the glass MRF machines. Moving to the right, the optical performance is fantastic, as I said, can be on diamond turning glass MRF. You have to specify it the right way. And material choices can be kind of limited. Diamond turning reflective optics is commonly done on either aluminum or nickel coated into nickel, which is really nickel coated aluminum. That's dominant, and not a lot of material choice for that. And as far as glass MRF, clearly, glass is your choice. So the third row, we have conventional glass polishing, which again can range in price depending on the complexity. Scalability is somewhat similar, maybe not as cost intense as some of the other methods, and high optical performance, but again, it's glass, so material choice is limited to glasses. This is where optical replication now on the last row really offers some great cost advantage, because whether it's low volume or high volume, the costs are quite competitive, and the scalability or ramping up is much more straightforward and streamlined. I have 3 stars there, so everything's on a scale of 1 to 3 if you haven't noticed that yet. So we think optical replication has a 3 on the 1 to 3 scale. And performance, you can see that we claim that optical replication can maintain the performance of diamond turn and all these other nicely figured mirrors, and we'll prove that and show that in the upcoming slides. Material choice stands out as well because we can make a replica onto virtually any substrate material that you require, and we'll show some of those examples as well as we move forward. So we think there's a lot of strength here with optical replication, and it's again a great way to leverage some of these very nicely made optics nowadays. Here's another view of explaining the way to take advantage of replicated optics. On the top half of this diagram, we have some very expensive, high cost, low volume methods of fabrication, and from that, by applying the optical transfer process, out comes these different types of mirrors: gratings, retroreflectors, aspheres, etc. It's a different way of looking at the process and how we leverage it. I really like this example a lot. This is a pretty unique application of replicated optics here. So you can see in this image there are two mirrors, a primary and tertiary mirror. That was probably diamond turned, and what's nice is these two mirrors are pre-aligned already when they were first made, and we simply made, as being replicated, it's you're replicating the alignment of the two mirrors at the same time. So it's a monolithic structure, has two aspheric surfaces. They're pre-aligned to each other, and they're pin registered. So you can see the assembly on the right. Many of these assemblies, I believe hundreds of these were made. So this is a telescope, a 3-mirror anastigmat, and you can see the primary, secondary, and tertiary mirror in the assembly. And very clever, I think is a very clever application of a replicated optic. As we said before, one of the advantages of going with replicated optic is the material choices. So aluminum, glass, any type of metal actually, and any type of glass. And also notice the shapes. We probably have even more exotic shapes that aren't on this slide, but not only just the shapes that can be easily made, but the mounting features. You can place them however they need to be to fit into your instrument, and it should aid in instrument assembly quite a bit. Deep UV applications is really where the replication process can help. As you know, in the infrared, many times diamond turn optics are fine for the infrared, near infrared, but for deep UV invisible applications, the periodic structure is a problem. So replication can help there. We'll get into that a little bit more. We have some good examples of that as we move on. As I said before, materials that you can replicate onto include the glass, different glass types, metals. These are all materials that we have replicated onto in the past. And basically with today's modern adhesion promoters, it really opens up the doors to applying the transfer layer to any substrate material you choose. While we're on the topic of materials, we want to make it clear that the optical transfer material we use is a low outgassing material. These are the test results from two separate independent laboratories, and there are two different types of measuring outgassing. And the second column says screening level. That's actually the NASA requirements. So in order to be space qualified, we need to meet those requirements, and you can see the results on the right. This is also not just applicable for space, but vacuum UV applications. Anytime you're worried about outgassing, vacuum applications are very sensitive, so it applies to that as well. Oh, now we're going to get into some fun stuff. This is where it gets good. Let's share some data, and just kind of show you what we've seen, and show you what to look out for. So let's start out with a typical diamond turn mirror. So this is very common. Diamond turning. You have I can't call them machining marks, but a periodic structure, and this actually, you can see this with your eye when it's at this level. But I guess the point I want to make here is notice the surface roughness of this scan. This is taken with a white light interferometer, and we're looking at around 2 nanometer surface roughness. Now, we have many customers who tell us that 2 nanometer surface roughness would be great. That's plenty good for us. But the truth is, it ends up not being good enough if it looks like this, because you're going to get a lot of color. Like I said, if you can see it with your eye, your instrument's probably seeing it. And let's take a look at the next slide, where we can actually see a line scan with a peak to valley of about 10 nanometers. Those are pretty deep structures, and it's periodic. That's what the killer is. It's a periodic structure. So in most cases, almost all cases in the UV and visible, this isn't gonna work. So what we'd like is a much smoother surface, and I think the next slide might show a post-polished diamond turn mirror. So this is greatly improved. You can see the in a 3D image, those peaks are knocked down considerably, and the surface roughness is now 1.2 nanometers. Very respectable number. I mean, that should be a nice shiny optic. The truth is, even by eye, if you look hard enough, if you look at this mirror, if we were able to share it with you right now, you can still see a little bit of color. And I guarantee if we can see it with our eye, your UV or instrument or spectrometer, wherever this is going, is also going to see it. On this next slide, I wanted to show this just to kind of show off the fidelity of the replication process. If you look closely, you can actually see the polishing marks from this is an off-axis parabola on there, and inherently has polishing scratches in it, or artifacts. And this is a replica from it. So these are very tiny features that are being transferred. So just showing off the high fidelity of the optical transfer process. Again, these are atomic force microscope images of diffraction gratings, which we've produced for many years. You can see these submicron features are really nicely shaped. The shape of these grooves is extremely important for the performance of a diffraction grating. If these grooves are distorted in any way, the performance goes down quickly. Again, just another image, close-up image of an optical surface with very high fidelity. Here's the first case study we're going to dive into. This was an ellipsoid mirror that a customer came to us looking for some help. They were actually having this, they need to keep the cost down, so they were having it diamond turned into aluminum and then subsequently post-polished, because it's being used below 200 nanometers. So they had to get rid of the periodic structure. So they had, I mean, aluminum's not easy to polish. You can see the result here. It looks kind of rough. It's about 80 angstrom surface roughness. And if you look at the aperture, so this is an ellipsoid mirror, so we've got a point source trying to get re-imaged through a 2 millimeter aperture on a white card, and you can see how much scatter there is around that aperture. Those are lost photons. That's scattered light that's not going where you want it to go. The customer said that, or claimed that, batch to batch this gets better or worse, probably because it was hand polished, but this was a problem for them. So our solution was to have a post-polished, let me back up, a diamond turned part into nickel. So it's diamond turned into nickel, and as many of you might know, nickel is a nice material to diamond turn into, but it can also be post-polished to a very high degree. And so we start with that master tool, and we make copies from that using the replication process. Now, in this exact same setup, you can see the light, nearly all of the light going through that aperture. 17 angstrom surface roughness, is quite satisfactory. This is a randomized surface as well. I think you can see that the periodic structure isn't there. So this is a nice example of a randomized post-polished nickel surface. And the customer reported a 2 or 3% increase in reflectivity as well. So happy all around. And we've been making hundreds of these for many years now. So this is my segue into the off-axis parabola section. I wanted to just first talk about the way these are being measured, so there's no ambiguity, so you guys understand how these interferograms are coming about. It's a common double pass setup for off-axis parabolas. Collimated light goes into the off-axis section. It focuses onto a retroreflecting ball, and that ball redirects the light back onto the parabola. And so it is a double pass setup, which is pretty sensitive. A fringe equals a quarter wave in this case. So in our first example here, this is a typical parabola that we deliver. Very respectable near 10th wave peak to valley performance. I know a lot of people like to speak in RMS terms these days, but I think all these slides are going to be peak to valley. The diameter of this part is about 60 or 65 millimeters, so it's a respectable size parabola. And again, we are delivering many of these. We deliver hundreds of these every month, actually. Here's a bit larger off-axis parabola, nearly 90 by 90 millimeters. And in this slide, the left-hand view is the master tool, and the right-hand view is the replica from it. And as you can see, it's not perfect, but it actually holds the shape pretty well. The target value, the customer needed 8th wave. It's a pretty good sized parabola. It's actually, this is a square inscribed in a larger circle. So, I don't know what the cross section is, but it's probably 4.5, 5 inches in diameter. But as you can see, we're preserving the wavefront nicely, met customer specifications, and we're happy with that. It is common for us to get requests for plain mirrors being replicated onto aluminum mostly, sometimes stainless steel. For FTIR instruments, they have a moving mirror, so I think that might be what this goes into. One of these does. The aperture here is about 40 millimeters in diameter, but nearly 20th wave, peak to valley. When you talk about RMS numbers, it blows my mind. This is like 100th wave RMS. It's like Unbelievable. But yeah, also another periscope mirrors. They call them tank mirrors sometimes. Are often plane surfaces replicated onto metal. And we'll get into the benefits of replicating onto metal again. But this is the results. But again, the application's really smart because we're replicating a plane surface onto a mountable metal substrate that just pin registers, bolts in, and they're off and running. There's no need to bond a piece of glass to a metal bracket and then bolt it in. It really is a streamlined component for an optic. Case study 2. I think this is my favorite case study, you guys. The F1 concave mirror. This is pretty tricky. The customer came to us, and there was a lot of dialogue that happened before we all thought it. Well, they were skeptical, and I have to admit we weren't exactly sure how well we could do on this, but it came out great. The substrate material had to be aluminum. They're adamant about that. It had to be replicated onto aluminum. Had to have like 10th wave peak to valley, super low surface roughness, and they're pretty much asking for the limits of what could be manufactured these days. They tried diamond turning, didn't work out for them. We also, we through dialogue understood why, and I think the customer realized replication was the best fit process. They came to us and said, "Hey, we think replication is the way to go." So we went forward, and here's the surface figure, and you can see it came out nearly 10th wave peak to valley. Their spec was an RMS spec, and we've got some really nice surface figure here. This it's about a 2-inch diameter part. And I think on the next slide we've got the roughness, which was the next critical specification. I mean, you can just see from the phase map on the upper left that that's just a beautiful smooth surface to I know it auto scales, but that's just a really nice looking white light scan. So 6.2 angstroms here. That's actually RMS. If you go average surface roughness, it's half a nanometer. But really pleased with that result. So in summary, there's a picture of a concave mirror. Doesn't that look exciting? They all kind of look the same. I've seen one, you've seen them all. But I thought it was worthwhile to throw the image of the concave mirror in here. I gotta have something to fill the graphic. But anyway, yeah, I actually added a row because their specification was 25 nanometers RMS surface irregularity. It translates to less than lambda over 25. That was their requirement. That's RMS again. It's not peak to valley. Their requirement was RMS. But and you can see we clearly exceeded that surface irregularity as well as the surface roughness. They just wanted less than a nanometer. We're able to deliver 6.2 angstroms of surface roughness. So I really think that I'm convinced that replication was the only way to get this. If you had to have this diamond turn and post polish, that could be done. Perhaps I think just imagine if someone was going to diamond turn this part and then get rid of the post polishing marks. I think it'd be really hard to get the surface figure or maintain the surface figure. That's one of the, I say, scary or nervous parts about any post polishing process is the ability to maintain the wavefront. It's a really special skill that doesn't come quickly. But anyway, even if these had to be diamond turned, you couldn't order these in high volume. It's just not cost effective. It's not scalable for production. So we were really pleased with how this one came out. So speaking of scalability, this is my segue slide to that topic. What more can I say? Well, I'm going to dive in right now. Here's an example of it's actually a freeform mirror we did started a few years ago. A little background on this mirror. These freeform mirrors were less than lambda over 10 peak to valley. That was a requirement. Less than 10th wave peak to valley. These are biconics with aspheric terms, or it was a biconic mirror with aspheric terms. But and when we talk about ramp up, it also you have to think about metrology as well. So it's one thing to make a bunch of mirrors because the replication process is very streamlined. Once you make the first few, it's easy to just scale up and make lots of them. But the metrology is critical. And as we'll find out later in this discussion, the metrology for freeform mirrors can be pretty specific and a little bit more involved than standard A-spheres. Generally speaking, though, productions for scaling up the replication process, it's not reliant on capital investment. Optical replication is much more streamlined for high production volumes, and really production times for direct manufacturing probably just make this not even feasible to make this part and deliver it in these quantities. This is an example of a diffraction grating ramp up. It's really no different than any other mirror. The process, the replication process, is really the same for mirrors or diffraction gratings. What we wanted to really point out here is that the timeline's 2 years, and we were moving along quite nicely after ramping up to over 1,000 pieces a month, gradually going up towards 1,500. Their customer had got 2 big contracts, and there was a huge spike in demand, and they just wanted to flip the switch and get rocking and rolling right away. It was kind of challenging, but we got there. You can see in this timeline from month 15 to 17, we almost quadrupled our output, and it just demonstrates how scalable this process can be. And ultimately, we were delivering 5,000 units a month on this part. But I think I've made my point there. So what we really want is designers to recognize that they can apply replicated optics or decide to go with a replicated optic for their A-spheres and freeforms during the design phase. Plan on that and you know, talk to our sales team, get some quotes, and share with us what you're trying to do so we can help lower your costs. We've seen a lot of examples. We've worked with lots of customers. We've helped them reduce cost. And so I'm going to try to provide some guidance here on that. It is really good to leverage the advantage of replicated optics early in the design phase so that optomechanical features can be determined. I know a lot of people who put parabolas into their systems always put a wedge back parabola in, but a parallel back parabola is much more cost effective in manufacturing and much easier to make. Again, we are transferring a nice parabolic surface or any surface onto a low-cost substrate, and the cost of making a parallel back parabola, which is actually it's probably a picture of a parabola you're looking at right now on this slide. The parallel back is much less expensive than a wedge back part. So, but you got to know that up front. We've had customers design wedge back parts and they can't change. So, well, it is what it is, and we'll deliver what you need. So generally speaking, the list you see on the slide here are all the things that the designer considers in his work, and I just want to make sure that you're communicating with the manufacturer, because every process, every technology has its trade-offs, and you know, we'd love you to use a replicated A-sphere, but let's make sure that we can match your requirements. And these are all the things we recognize that need to be considered. I'm sure you have even more things, but mounting is important. That's a huge topic. You can't believe how many times we've delivered a 10th wave optic, and just the mount distorts it. It's amazing how little pressure it takes to distort a 10th or even quarter wave optics. So we encourage talking to the manufacturer, that'd be us, early in your process. Get us involved, ask us questions, and make sure it's a good fit. Metrology, that's an important topic. We have the typical things that most shops have to measure conventional optics in the 21st century. We have atomic force microscope, white light interferometers, conventional interferometers. So we measure reflectivity from our metal coatings. All the typical things that, and we're happy to share data with all of our parts. Some of our parts we measure 100% of, some we sample. Depends. It really depends on the part. Every part's different. All the optics we make are custom optics, because some customers require more metrology than others. But the bottom line is we want to make sure that you're getting the right part every time, as always. So moving on. Oh yes, freeform mirrors. This is a hot topic lately, and it makes sense because it really is the next evolution of optics. Excuse me. A-sphere has been made now for several decades, and those have been well applied, well understood. Freeforms is the next evolution because you can combine two corrective surfaces into one. There's actually even more advantages other than just that with the freeforms. I think we touch on that a couple slides from now. Here's some surface equations, freeforms. The definition of a freeform is, I don't want to say it's hotly debated, but everyone kind of throws their own spin on it, it seems. But I think it's generally accepted that it's a non-rotationally symmetric surface, so there's no rotational symmetry in any axis. I actually, someone once recently told me a toroid was a freeform, but in my head I can think of two axes of rotation, so I don't know if I believe that. But one thing I do know is that with any freeform I've ever encountered, you can't measure it on the interferometer in a conventional manner. You can't do it with on first principles. You can't illuminate with a collimated light, with a point source. It takes a special null optic to measure a freeform mirror. It's hard to put that into a definition, but I just want to give you the feel for how freeforms are very different. So there are, I say, many advantages, and it's really nice as an optical designer to have this freedom to use a freeform mirror. Clearly you can shrink the system if you reduce the optics, less scatter, decrease the number of optics, lowers cost. You can usually they're used for improving the performance, and many times you can do both. Reduce the size, increase the imaging performance, and maybe you just increase system throughput. There's a lot of advantages, and it's up to the designer to decide which one's the most important. So So we've got a few categories here of freeform mirrors. It's interesting to note. I don't know how many people know this. I think it's kind of a fun little side note that remember the Polaroid SX70 camera from the 1970s? That had a freeform mirror in it, and it was a hand-figured mirror, and that mold was tightly or extremely guarded by Polaroid. And for me, that's the first application of a freeform imaging mirror that I even know of. But back to our slide here. Non-imaging applications have been using freeform mirrors for some time. Laser beam shaping. They make little small lenses that go in front of the for laser machining to shape the beam, and makes square beams and all kinds of whatever shape they need. And for illumination, your headlamps on your car. Those reflectors in the headlamps of your car are all freeforms, and they've been doing that for decades. So those are non-imaging applications where they're mostly energy gathering or energy distribution type applications. But for imaging optics, that's where the new topic is here in the 21st century with freeforms. The imaging applications now with these with the CNC machines that are available now with the feedback loop and the word escapes me right now. They're able to do some really exotic optics, and there's more and more examples coming out every year of how freeforms are enhancing some of these high-end instruments. But they're very expensive because they only make a few. They're low volume at this point. I'm not aware of really a mass-produced, other than what we provide, a mass-produced freeform mirror. So that's where we want our technology to help bridge that gap. So sometimes I'm asked, what are the design limitations for a freeform mirror? And really, I think the only thing I can think of is perhaps steep curvatures. Steep curvatures can sometimes be challenging to make and even more difficult to measure sometimes. And when I say steep, I'm thinking like 45, 50 degrees. It doesn't mean it can't be made, but if you're going to put it in front of an interferometer, you have to get the light back to go back into it. So with that said, the truth is, in all the freeforms I've seen for imaging application, it's just a few microns of departure or less that's required to make the corrections you need. So these don't need to be drastically crazy shaped mirrors. But once you get your design in hand, it's really important to start talking to the rest of your team about the optomechanics, and other aspects of how you're going to integrate the freeform mirror. And I'll move on to the next slide. And one of the reasons it's really important to start I say really important to start communicating early with all the teams, your optomechanical guys, your manufacturers. Share your idea for this component, mostly the sag table, the all-important sag table. I can't emphasize it enough. How does the manufacturer verify they came up with the right surface for you? It all points back to the sag table. You got to make sure, clearly the surface the manufacturer makes has to meet the expectations, and the sag table needs to not only to relate to the fiducials or datums of the part. We want to make sure everyone gets the same sag table. So we like to take the surface equation, generate our own sag table, get back to the customer, make sure it matches. And if we have a vendor that's making a part for this, we have them generate their own sag table. This is actually, this method of independent verification was adopted after a few mistakes had occurred, and thank goodness we caught them in time. It's possible just to mess up a sign convention or your starting point on the array. We've seen this happen, and it's really important to make sure everyone's on the same page with the SAG table and the fiducials to make sure that the pin registration is just right, etc. So in measuring freeform mirrors, different techniques will be used at different points in the process typically. Many times almost always in our case, for the prototype runs, we use a contact probe or non-contact probing method similar to what you see here, because it's just you just need a few measurements to verify the surface. And once we get into production, higher volume production, we really like to use a CGH. You could use stitching interferometry as well. That's perfectly acceptable. We don't have that, but that's a viable method. And but the CGH is quick once it's set up. I mean, it ends up being a dedicated interferometer for that part, but because the time it takes to set up each CGH, we just dedicate an interferometer to that part number, and it goes real quick. And again, here comes the SAG table again. For the non-contact or for the probing methods, they actually input the equation and or the SAG table to make sure their probe gets a rough idea of where it should be, and they also compare it to the theoretical model and show the departure. Yeah. Oh yeah, and the fiducials. That's right. It's really important. I don't know if I talk about this later or not, but I must bring it up now. The fiducials that are needed for measurement are the same ones that we'll use for manufacturing, and we hope they're the same ones that the assembler uses during their assembly. It's really almost I can't say vital, but you don't want to have different fiducials for different parts in the process, otherwise you get tolerance buildup. If we can use the same fiducials that the end user is going to use to align the optic in their system, it really makes for a much more precise part. So again, that's where the early communication is important. Make sure that the datums and fiducials that the end user is going to use work with the manufacturing. Wow, that brings us to the end so quickly, so soon. We were having so much fun. I could talk about this all day, you guys. So, but anyway, summarizing remarks. So we want to make it clear that replication can significantly and does significantly reduce the cost of A-spheres and freeforms. We see it every day. We're doing it here. It allows scalable mass production, highly customizable for material choice, unusual shapes and mounting features. Inherent in the process is minimum part-to-part variation. These really exotic optics are, if you had to make all originals or in batches, the batch-to-batch variation is usually noticeable. With the replication process, it's virtually indistinguishable. So we believe that for all these reasons, it makes freeforms more accessible than ever before. So thank you guys for joining us today. And thanks again for the folks at Electro Optics for arranging this. And with that, I'll hand it back to the team for questions and answers. Thanks again.